xz function of vector?
Yeah, sorry, this is xz. Yes, thank you. So let me bring up something here. I want to show you one of the formulas that we were working with when it came to this whole idea of flux. Right here. These are the formulas I gave you, right? And we keep on trying to use this one right here. Yeah? But this came from this idea. This was the idea that kind of motivated it all, right? Was we're going to take the component of f onto n, which was dotting those two, and then multiply that times this infinitesimal surface. I'd like for us to consider this formula again right now, okay? And I'm going to go back to the example right here. If we consider the surface integral of S1 as being f dotted with n ds, then we know f is that field up there, right? PQR. The normal vector of this surface, right, is easy because it's a plane, right? Because this is a plane, the normal vector, all of these vectors, right? What are they? 0, 1, 0, right? Always, no matter where you are on this surface, the normal vector is always this. So imagine now that I take the field, and my field is 0, y, negative z, right? And imagine I dot that with that normal vector, 0, 1, 0, ds. Then what do I wind up getting here? What's that dot product? This is this y ds, right? However, because this is a plane, right? We know that the y coordinate is always what? The y is always 1, isn't it? So that actually becomes, I'm running out of room here. I'll just do it up here because we're going to wind up not using that one or this one, okay? Because I don't want to go to polar. I'm going to go from here. This is just this. And what is that? That's the area of S1. Because it's the double integral over S1 of 1 ds. 1 ds is the surface area of S1. Do you know the surface area of this disk? Well, do you know its radius? You should, right? It's x squared plus z squared equals, well, less than or equal to 1 gives you the whole disk, but that means the widest, the radius is 1, right? So this is equal to the area of S1, which is equal to pi times the radius squared, which is just pi. And we never did any work, right? Like we never did any real work, right? So what this is telling you is that you always have to be paying attention to what you're working with. Yes, we could have done R of UV in the beginning, we could have done crossed and all that. We could have worked through that. But if we just back up and realize that a plane always has the same normal, then we could go back to this formula, and then things just worked out real nice, didn't they? Okay, are we done? Nope, we're not done. Okay, so now we need to look at S2. So on S2, can we play the same game on S2? Are we going to get lucky that we can do the same thing we just did here on S2? No. Why not? Why can't we? Yeah, it's not a flat surface. Our normal varies through the surface. So we can't just stick a vector in there and say it's always that. So since we can't do that, if we're trying to do S2, again, we have options, okay? We have many options. So can you look at S2 as being a function of two variables. Yeah, this is what I had written earlier that I messed up. So this right here, we can look at that as the y being a function of x and z, and it is exactly the paraboloid, right? Like that. And we know our field. Our field is 0, y, negative z, right? So once we know our field and we have our surface as a function of x and z, I can go to which formula here? E, F, G, H are your choices. G, right? I can use the G formula with one slight change. We got to multiply by -1 because our normal vectors need to be coming out the left side. This formula works if your normals are growing out the right side. So the formula that I'm about to use is the double integral over d of not negative p, but p partial g with respect to x minus q, and then plus r partial g with respect to z dA. Y'all agree? Now we're going to run into a problem again, because when we're looking at the domain here, our domain involves the variables x and y, and that is the shadow of this thing on the xz plane. Did I say x and y? Function of x and z. That is the shadow, and that's still going to be a circle. We're still going to need to go to polar, okay? But we didn't have a fixed normal for this one. It wasn't a plane, so we have to do it. Let's go ahead and crank this out. Double integral over d. Now p for us is 0, so it's gone, right? So this is gone. And then y, q is just y, but it's negative, right? So negative y. But what is y? Let me write it down first. Negative y, that's this piece, right? This was 0. And then plus r, which is pqr, negative z, times the partial of g with respect to z, which is 2z dA. Any questions there? So the first part was gone. Now I have to replace what with what here? Y with x squared plus z squared, because you can only have x's and z's in here, right, if we're going to use this. So this should become double integral over d of negative x squared minus y squared. The negative goes to both, right? And this will become minus 2z squared dA. And now we get to go to polar.
Should be negative x squared, negative z squared.
Yeah, it should be. I don't know. Yeah. Well, I guess today is just going to be one of the days. These are little things, but they're big things, right?
Yeah.
All right. We good? Yeah. All right. Now we can put that together. We get -3 of those. Yeah, I guess I should. Let me just do that. Let's put those together. So negative, ooh, that doesn't work very good. Negative, you know what? Do we want that? You know what? I'm not going to do it. I'm going to leave it apart for a second. And the only reason I'm leaving it apart is because I'm going to be going to polar. Right? I'm about to go to polar.
Oh, yes.
Because our xz, the shadow of this thing on the xz plane is that circle. So now I go to polar. And to go to polar, I need to make my conversion that x is going to be r cosine theta. And my z is going to be r sine theta, because we're working with x and z, not x and y. Our Our r will go between 0 and 1 because it is has a radius of 1, right? And the theta will go from 0 to pi. And by doing it that way, this integral now becomes 0 to 2 pi, 0 to 1. Okay, so I left this alone because that right there, when I factor out a negative, will become negative r squared. Okay, so I have negative r squared. And then I have minus 2 times what's z squared? I got to square the z, so r squared sine squared theta, and then times r, right? Don't forget the r, dr d theta. So you can work that out, right? That should go pretty easy, I think. Again, that's all within reason. Okay, you wind up getting negative pi here. And because you get negative pi, now you add that to the answer we got for S1, so your answer is 0. So your flux is 0. So at the end of this all, the net flow is 0, right? There's some flowing off, out of one end, or one part of it, there's stuff coming out. The other part, there's stuff going in. Together, your net flow is 0. All right, what do y'all think? This all seem all right, or? How about we work on this, or you work on this? I let you all work on this, give you some time to work on this one. All right, and we'll see what we'll do is we'll have volunteers again, like we did last time, but we'll have different volunteers. So we need new people today. Not because you did a terrible job, but I want everyone to play. All right, how many surfaces do we have here? Find the flux of the vector field x squared, y squared, z squared. You can have someone from your table. Just different, different presenters, that's all. We have the vector fields given. The surface is the boundary of the solid half of the cylinder. 0 less than or equal to z less than or equal to square root of 1 minus y squared with x bounded between between 0 and 2. So almost looks like a little aircraft hangar. You've got this, right? You've got the back side of it. You've got the green curved part of it. And you have the bottom part of it. So there are 4 surfaces that need to be considered here. All right? Going to let you all play with that? Okay. I'll give you all some time. What do you say? The goal would be for you to get at least 2 of them done. 2 of the 4 surfaces, get them done in the time I give you. And I'm going to give you like 3 minutes.
Actually, I do have one thing I need to add.
Yes.
Can you make some of the kids really see the axes that well? Is it okay if you make the shape a little more clear, or so we can see like which axis it's
Well, I'll tell you where it is. This is, well, let me turn it a little bit. That didn't help much. So your z is obviously up and down. This is your x, and this is your y. Is that what you're asking me?
Yeah.
Okay.
That's all I wanted to ask. That's all.
Okay, I was kidding about 3 minutes. I'm going to give you all, let's say, 20 minutes. See how far you can get in 20 minutes. And help each other out. Talk to each other. you know, see how you get. Yes.
So I guess like the app equation with the flux.
Mhm.
Like that's what gives you the answer. But like, what is the total goal of these?
What is the what?
Like the total goal. Like what when you get these answers, like what does it mean? Exactly?
Well, it depends on which of these you're talking about. Like for these first, this one, this one, this one, and this one. Those are all surface integrals. There's no vector field at all anywhere. So let's say, like one specific example would be if this was our density function. So it's giving you the density at every point on the surface. Then this would represent the mass of it. Is that what you're getting at? Like what? So look in a math class, we're concerned about the math. You go and use this in a certain class, then that function has meaning, right? That f of x, y, z. Depending on what that is, your answer will represent different things. So you could have that it's giving you the charge density at every point on the surface, how much electrical charge there is there. Then this would give you the total charge on the surface. Does that help?
Yeah, that makes sense.
Then that's A, B, C, D. Okay. Now E, F, G, H is now the flux is the example that most people can understand. You have like water flowing through the surface, so you're trying to get the net flow through it. But you again could have an electromagnetic field where this is a force, a force like a magnetic force, and so it's giving you what in physics they call the flux, which is your net electrical flow through the surface. Is that helping? Okay. That's the thing, in math, it's general. So our answers are going to be numerical. Later on in some other class, that number will be attached to some unit. And that unit will be whatever it is you're talking about. Does that help?
Yeah.
Okay. All right.